Picture this. You're floating in crystal clear water, the sun filtering down through layers of blue. But something is wrong. The water around you begins to darken, not from clouds above, but from something massive rising from the depths below. A shadow longer than a school bus, wider than a highway lane, moving with terrifying purpose. What you're witnessing isn't from some Hollywood nightmare. It's a glimpse into Earth's prehistoric oceans, where creatures so massive and so deadly roam the seas that they make today's great white sharks look like goldfish. For hundreds of millions of years, our planet's waters have been ruled by predators so alien, so perfectly engineered for killing, that they challenge everything we think we know about the limits of life. From sharks with circular saws for mouths, to marine reptiles with bite forces that could crush cars. From armored fish that could slice through steel to whales with teeth longer than your arm. These weren't just big fish. They were evolution's most successful experiments in aquatic terror, apex predators that shaped entire ecosystems through fear alone. But here's what's truly chilling. Many of these monsters didn't just hunt smaller prey. They hunted each other. In the prehistoric oceans, being the size of a whale wasn't protection. It made you a target. Today, we're diving into the abyss of Earth's history to meet the most terrifying ocean predators that ever lived. Prepare yourself for a journey through 500 million years of evolutionary arms races, where survival meant being bigger, faster, and deadlier than anything else in the water. The ocean has never been safe, but you've never known just how dangerous it could be. Chapter 1. The Birth of Oceanic Terror. Imagine a creature emerging from the shadows of an ancient sea, its massive head covered in bone armor so thick it could stop a sledgehammer. No teeth instead, razor-sharp bone plates that never dulled, never broke, self-sharpening with every bite. This was Dunkleosteus, and 380 million years ago, it was the undisputed ruler of Earth's oceans. The year is 380 million years ago, during the Devonian period. The continents look nothing like today's vast shallow seas cover much of North America and Europe. In these warm, oxygen-rich waters, something unprecedented is happening. Life is conducting its first experiment in creating the perfect oceanic killer. Dunkleosteus. Torelli was one of the first true apex predators to appear on Earth, meaning it could eat any animal it wanted and had very little predators. But calling it simply a predator doesn't capture the sheer terror. This creature represented picture a school bus with armor plating and a mouth that could open wide enough to swallow a small car. Due to the armored body, the Dunkleosteus probably swam slowly. However, they did not have to worry about attacks from other animals apart from other Dunkleosteus. At that time, they were alpha predators, located at the top of the food chain. The most remarkable thing about Dunkleosteus wasn't just its size-reaching lengths of up to 33 feet, but its revolutionary approach to killing. This fish, although powerful and carnivorous, had no teeth, but sharp bone plates that formed a kind of beak. This weapon was one of the strongest and best killing machines, bony plates making up. The jaws were sculpted into fangs and long slicing edges. The upper and lower jaws would also shear against one another, causing them to self-sharpen. This was evolution's first attempt at creating a biological chainsaw. Every time Dunkleosteus closed its mouth, it literally sharpened its own weapons. The numbers behind this creature's bite are staggering. Anderson and Westneat studied the feeding mechanics and the bite force of Dunkleosteus torelli jaws. They made two key findings. First, they discovered the jaws could rapidly open and close, so fast that Dunkleosteus could make a suction when opening, sucking prey into it. Secondly, they found the jaws to have a tremendous bite force, on par with giant crocodiles. The bite force was almost 2 tons. Some scientists estimate that it was over 3 tons. This would mean that the bite force was similar to that of the T-Rex and greater than that of modern saltwater crocodiles. But unlike T-Rex, which would appear 200 million years later, Dunkleosteus combined this crushing power with lightning speed. Putting this in terms of pressure, this is 147 million pascals, or 21,000 psi. Combined, Dunkleosteus could suck in and bite straight through any animal alive at that time, from the thick-shelled ammonites to other placoderms with body armor. The fossil evidence reveals something even more disturbing about these armored killers. Since it was one of the largest representatives of predatory fish in history and the owner of incredibly strong jaws, it could afford almost any nutritional whim. Dunkleosteus ate everything he could catch. He did not even shy away from cannibalism. The bite marks on the skeletons of Dunkleosteus testified to this. A study by Hall et al. 2016 found scrape and puncture marks on other Dunkleosteus armor that were made by larger Dunkleosteus. This means they may have even eaten each other. When you're powerful enough to bite through any armor on Earth, even your own species becomes prey. The hunting strategy of Dunkleosteus was as efficient as it was terrifying. Apart from a strong grip of its jaws, this fish could open its mouth at a speed of 1/50th of a second, which generated a powerful suction force. Thanks to this, she could simply suck in her victims. Imagine the scenario. You're a fish in these ancient seas, and suddenly the water around you begins moving. Not a current, something is pulling you. Before you can react, you're being sucked toward a mouth lined with bone blades, moving faster than your eyes contract. Another interesting fact is the jaw shape of Dunkleosteus changed as it grew from juvenile to adult. A study by Boyle et al. Showed the jaw became more elongated and grew a longer anterior fang, or cusp. The study concludes as the animal grew, the diet shifted from soft-bodied prey, such as fish and sharks, to larger armored prey, such as placoderms. This reveals something crucial about Dunkleosteus. It wasn't just a mindless eating machine. It was sophisticated, adapting its hunting strategy as it matured. Young Dunkleosteus picked on easier targets, while adults graduated to the most dangerous prey in the ocean, other armored predators. The fossil record shows evidence of this escalating arms race. Partially digested, return parts of other fish were often found near the skeletons found, suggesting that Dunkleosteus ate greedily and was unable to digest the bones. These ancient seas were becoming killing fields, where even the apex predators sometimes bit off more than they could chew. Literally, Dunkleosteus represents a crucial turning point in ocean evolution. This heavily armored fish was one of the world's first open ocean predators, filling a niche now occupied by great whites and orcas. But unlike anything alive today, Dunkleosteus combined the durability of a tank with the killing power of a hydraulic press. The very existence of Dunkleosteus tells us that Earth's ancient oceans were far more dangerous than we ever imagined. This wasn't just a big fish. It was evolution's first attempt at creating an unstoppable oceanic killing machine. Armored fish, Placodermi, reigned relatively briefly on our planet. They lived from the late Silurian to the end of the Devonian, 430 to 360 million years ago. But their brief reign had lasting consequences. The arms race that Dunkleosteus started, the drive to become bigger, more armored, more deadly, would continue for hundreds of millions of years. Every subsequent ocean predator would be judged against this standard. Can you survive in waters ruled by creatures that can bite through steel? As we'll see, the answer to that question would drive evolution to create monsters that make Dunkleosteus look almost gentle by comparison. The armored nightmare of the Devonian was just the beginning. The real terror was yet to come, in the form of creatures that abandoned armor entirely in favor of something far more dangerous: speed, intelligence, and teeth designed for one purpose only: killing other killers. Chapter 2. When sharks became monsters, what's the buzz? It's all about Helicoprion, dubbed the strangest shark in Earth's history. But this wasn't strange in the way a quirky animal might be strange. This was strange in the way a nightmare is. Strange, defying every rule about how mouths and teeth should work. Picture a shark 25 feet long, cruising through the ocean 270 million years ago. But as it opens its mouth, instead of rows of triangular teeth, you see something that belongs in a sawmill. A perfect spiral of razor-sharp teeth, rotating like a buzzsaw, designed for one thing, turning soft-bodied prey into shredded meat. 4. Over a century, paleontologists stared at fossilized tooth whorls and tried to make sense of what they were seeing. Russian geologist Alexander Petrovich Kabinski coined the name Helicoprion in 1899. Even though the coiled fossils superficially resembled the shelp, ammonites and nautilus paleontologists, often found in the marine fossil record, Karpinski, realized that the petrifications were actually part of a shark-like fish. But where did these spirals belong? Over a century of speculation produced visions of sharks with whorls hanging off their snouts, lower jaws, dorsal fins, caudal fins, and even embedded deep in their throats. Scientists literally tried to put this weapon everywhere on the animal, except where it actually belonged. The confusion was understandable. Almost all Helicoprion fossils consist of spirally arranged clusters of fused teeth, called tooth whorls, which in life were embedded in the lower jaw, but a circular saw in a lower jaw. It seemed impossible. After over 100 years, the mystery of the Helicoprion jaw is solved. That doesn't make the prehistoric fish any less enigmatic. With only a single blade of teeth, how did Helicoprion actually catch and consume prey? The answer came from CT scans of well-preserved fossils. Contrary to the popular long jaw restorations, the tooth whorl of Helicoprion totally filled the lower jaw. The jaw joint sat right behind the weapon, and the spiral dentition was buttressed by jaw cartilage on either side. Even more bizarre, Helicoprion didn't have any upper teeth to speak of. The spiral of continually added teeth was the creature's entire dental armament. This wasn't a shark with some strange extra teeth. This was a living buzzsaw with a shark attached. Based on the new restoration, Tapanila suggests that the analogy to a circular saw is almost perfect. Not only was the tooth whorl shaped like a saw, but, Tapanila points out, as the jaw closed, the tooth whorl rotated the teeth backwards in a rotational saw motion. But this wasn't random destruction. It wasn't until the application of biomechanical principles that scientists were able to reveal how this predator consumed its prey. Amazingly, each tooth had a different function depending on its position in the tooth whorl. Anterior teeth hooked and dragged prey into its mouth. The middle teeth pierced and cut the prey, whilst the posterior teeth cut and pushed the prey into its oral cavity. Think about the sophistication of this system. A single jaw that could hook, slice, and push prey, all in one smooth motion. This unique feeding apparatus would have allowed Helicoprion to consume both hard and soft-bodied prey items using different feeding strategies. Such a strategy would have worked well on squid and other soft-bodied cephalopods of the 270-million-year-old seas. But Helicoprion wasn't just hunting random squid. It was targeting some of the most intelligent invertebrates that ever lived. While its whorl's similarity in appearance to ammonoids was actually a clue, the shape made it good for snagging ammonoid flesh and then ripping them out of their shells. As Ewing writes, the eminent French paleontologist Philippe Janvier likened the tooth whorl to a forked escargot, a snail fork. Imagine being an ammonoid, one of the ocean's most successful predators, protected by a spiral shell that has kept your kind safe for millions of years. Suddenly, you encounter something with a mouth that perfectly matches your shell's geometry, but instead of offering protection, is designed to extract you like a horrifying biological can opener. Helicoprion grew to an astonishing length of approximately 20 to 25 feet and may have weighed up to 1,000 pounds. But it wasn't just the size that made them terrifying. It was their distribution and success. Helicoprion existed in the days of Pangea, which explains the wide distribution of fossil remains across the globe. The only regions where they have not yet been found are South America and Africa. These buzzsaw sharks ruled virtually every ocean on Earth. Helicoprion whorls held about 180 teeth. Towards the base of the whorl were the largest of which, but they scaled down in size from there. Each tooth could reach over 4 inches in length, and the largest teeth possibly exceeding 10 centimeters, 3.9 in length. Unlike modern sharks that shed and replace teeth, Helicoprion had a different strategy. Helicoprion tooth whorl kept growing throughout its life, adding new teeth to the inner coil while older worn teeth were pushed outward. This meant that older Helicoprion individuals had increasingly massive and complex cutting apparatus. The teeth at the center were the youngest and had a hooked appearance. The others were older and had a triangular shape. The teeth grew bigger away from the center, with the largest ones being over 3.9 inches in length. Picture encountering an ancient Helicoprion, its lower jaw containing decades of accumulated teeth. In a perfect spiral, each one honed for a specific cutting task. The older the animal, the more deadly it became. Helicoprion fossils have been found all over the globe, as they survived the Permian-Triassic 280 million years ago, which wiped out 90% of species. These buzzsaw sharks witnessed the greatest extinction event in Earth history and survived it, thanks to its 360-degree spiral teeth and sheer size. This fish didn't have any notable natural enemies or threats. In a world where 96% of marine species were dying off, Helicoprion continued to cruise the oceans, their buzzsaw mouths still finding prey to shred. But even apex predators can't survive when their entire ecosystem collapses. The buzzsaw shark has not been around since the Triassic period, or about 225 million years ago. Along with Helicoprion, about 96% of the sea's creatures perished during Earth's largest extinction event, the Permian-Triassic extinction. Scientists generally concede that the Great Dying was triggered after a violent streak of eruptions in the Siberian Traps. As the volcanoes erupted, they released excessive amounts of carbon dioxide. In turn, ocean oxygen levels dramatically reduced as acidity levels skyrocketed. About 80% of the ocean's oxygen was gone, with some parts of the sea containing zero oxygen, especially the deepest parts of the seafloor. Even the perfect predator couldn't survive in an ocean with no oxygen. As a result, the majority of marine species from this period went extinct due to suffocation. Including Helicoprion. Helicoprion represents evolution's willingness to experiment with truly alien solutions to predation. While Dunkleosteus relied on armor and brute force, Helicoprion developed something far more sophisticated, a biological machine tool designed for precision killing. Although this fish is built like a shark, has a cartilaginous skeleton, and is often compared to sharks due to its apex predator status, Helicoprion is not related to modern sharks, nor was it in the lineage that evolved into true sharks. This was an entirely separate experiment in creating the perfect oceanic predator. The buzzsaw sharks proved that in the ocean's arms race, innovation could be just as important as size. But they also proved something else. Even the most perfectly adapted predator can be wiped out by forces beyond their control. As we'll see, the extinction that killed Helicoprion created opportunities for entirely new types of predators. The oceans were about to be repopulated by creatures that would make both Dunkleosteus and Helicoprion look primitive by comparison. The age of the marine reptiles was about to begin, bringing with it predators so large and so intelligent that they would redefine what it meant to be an apex predator. Chapter 3: Rise of the First Sea Monster. The giant marine predator was at least 28 feet, 8.6 meters long. Fossils showed. The carnivore was recovered over a course of 3 weeks in 2008 from what is today a mountain range in central Nevada and is now kept at the Field Museum in Chicago. But this wasn't just another big marine reptile. The 244-million-year-old fossil, named Thalatorchon saurophagus, lizard-eating sovereign of the sea, is an early representative of the ichthyosaurs, a group of marine reptiles that lived at the same time as dinosaurs and roamed the oceans for 160 million years. What makes this discovery truly remarkable isn't just its size, its timing. Remarkably, only 8 million years prior to the appearance of Thalatorchon, a severe extinction at the end of the Permian period killed as many as 80 to 96% of species in the Earth's oceans. Imagine an ocean emptied by the greatest mass extinction in Earth's history, its waters nearly lifeless, its food web shattered. Now imagine that in just 8 million years, a blink of an eye in geological terms, life not only recovered, but produced the first mega predator capable of hunting prey its own size. This is the story of Thalatorchon, the creature that proved life's incredible resilience and set the template for 160 million years of marine terror. To understand the significance of Thalatorchon, we need to picture the world it inherited. This animal occurs only 8 million years after the biggest mass extinction event in Earth's history, the Permian extinction, which literally wiped out up to 95% of all the species in the ocean. Bibish explained, "The ocean was a pretty empty place afterward. The Permian Triassic extinction, known as the Great Dying, didn't just kill most marine life, it reset the entire evolutionary game. The sophisticated ecosystems that had supported creatures like Helicoprion were gone. The oceans were essentially starting over, with only the smallest, most resilient organisms surviving. But nature abhors a vacuum, especially in the ocean. But not for long, the fossil record shows that species return quickly. The presence of a top predator like Thalatorchon during that time period shows that the system was intact within a relatively short time, since marine ecosystems build from the bottom of the food chain up, because it was a metapredator capable of feeding on animals with bodies similar in size to its own. Thalatorchon was comparable to modern orca whales. But this comparison, while useful, doesn't capture the revolutionary nature of what Thalatorchon represented. Named Thalatorchon saurophagus, or lizard-eating sovereign of the sea, the ichthyosaur is the first top predator in the marine food chain that fed on prey its own size, similar to modern orca whales. Think about this for a moment. For hundreds of millions of years, marine predators had mostly followed the same basic rule. Big animals eat smaller animals, even mighty Dunkleosteus. Despite its cannibalistic tendencies, primarily hunted creatures smaller than itself. Thalatorchon changed everything. It was the first marine predator, specifically adapted to hunt other large predators. It had a massive skull and jaws armed with large teeth with cutting edges used to seize and slice through other marine reptiles in the Triassic seas. But these weren't ordinary predator teeth. The teeth of Thalatorchon are an exception to the ichthyosaurian rule. Measuring about 4 inches tall, with a 2-inch crown, the largest Thalatorchon tooth is blade-like, compressed from side to side and bearing 2 cutting surfaces. The sharp surfaces are not serrated, but, in overall form, the dental armaments resemble the teeth of mosasaurs, large pliosaurs, some marine crocodiles, and one later ichthyosaur called Himalayasaurus tibetensis. All of these animals, paleontologists suspect, were marine macropredators. This convergent evolution is telling. Across millions of years and multiple lineages, Nature kept returning to the same dental design when creating predators capable of hunting other large predators. Thalatorchan was the first to perfect this template. It was about 8.6 meters long and was one of the earliest apex predators of the ocean after the Permian-Triassic extinction that could have fed on creatures of similar size to it. It filled an ecological niche similar to killer whales today, but unlike modern orcas, which evolved in oceans already populated by whales, seals, and other marine mammals, Thalatorchan was pioneering an entirely new ecological niche. It was the second largest marine macropredator, only preceded by the bigger Dunkleosteus around 140 million years earlier. The gap between Dunkleosteus and Thalatorchan represents one of the most dramatic transitions in marine predator evolution. The armored, slow-moving placoderms were replaced by streamlined, fast-moving reptiles with completely different hunting strategies. Where Dunkleosteus relied on armor and crushing force, Thalatorchan represented a new philosophy of predation. This fearsome ichthyosaur was the first of its kind to have 5-inch, double-edged teeth that it could use to kill larger prey than its future relatives like Symbospondylus. The ichthyosaur body plan was revolutionary. These weren't clumsy armored fish. They were marine reptiles that had evolved from land animals, bringing with them advanced nervous systems and sophisticated behavior. They developed streamlined bodies, powerful tails, and large brains capable of complex hunting strategies. Look into the petrified mouth of almost any ichthyosaur, and you'll find lots of simple, pointed, conical teeth. This is the dental arrangement of a grabber, a predator that catches small, slippery prey such as fish and squid. But Thalatorchan was different. Its massive, double-edged teeth were designed for something far more ambitious because it was a metapredator capable of feeding on animals with bodies similar in size to its own. Thalatorchan was comparable to modern orca whales. But what does it actually mean to be a metapredator in the Triassic seas? The new study does not present any direct evidence of ichthyosaur on ichthyosaur predation, but based on the anatomy of the newly described predator and the local richness of other marine reptiles, Thalatorchan may have been a top predator that was especially adapted to hunting other ichthyosaurs. This represents a fundamental shift in marine ecosystems. For the first time, being large wasn't necessarily protection. Size became an arms race, with predators and prey locked in an escalating cycle of getting bigger, faster, and more dangerous. The speed with which Thalatorchan appeared after the Permian extinction tells us something profound about life's resilience. Analysis of the remains showed that Thalatorchan was indeed a top-tier predator from the Middle Triassic period. Its teeth, which were incisor-like and featured 2 cutting edges, indicated a macro-predatory feeding style. And fascinatingly, the discovery of the extinct ichthyosaur shows how ecosystems can quickly bounce back from even the most extreme events, including mass extinctions. But this wasn't just recovery, it was innovation. The post-extinction oceans didn't just rebuild what they had lost. They created something entirely new. The rise of a predator such as Thalatorchan documents the fast recovery and evolution of a modern ecosystem structure after the extinction. Modern ecosystem structure meaning food webs with multiple trophic levels, including apex predators capable of hunting other apex predators. Our Jim was thus the first in a long row of T-Rexes of the sea, which is why we named him Thalatorchan, ruler of the seas, Sanders said. This wasn't hyperbole. Thalatorchan established the template that would dominate marine ecosystems for the next 160 million years. And, so far as we know, the long tradition of macropredatory marine reptiles started with a roughly 245 million-year-old ichthyosaur that bore a vicious grin, double-edged teeth. Every subsequent marine megapredator, from giant pliosaurs to massive mosasaurs, would follow the basic blueprint that Thalatorchan pioneered. Thalatorchan represents more than just the first mega-predator of the post-Permian world. It represents proof that life doesn't just survive mass extinctions, it uses them as opportunities for revolutionary innovation. The empty oceans left by the Great Dying became laboratories for experimentation. This is the first predator in a long row of predators down to this day. The players have changed, but not the game. The game that Thalatorchan started was simple but deadly. In the ocean, everything is prey to something bigger. And being big doesn't make you safe. It makes you worth hunting. The fossil of Thalatorchan, nicknamed Jim after its discoverer, represents a turning point in Earth's history. The fact that a giant predator capable of tackling similarly large prey arose so soon after the end Permian mass extinction reveals that ecosystems recovered rapidly after the die-off. But Thalatorchan was just the opening act. The template had established large, intelligent marine reptiles capable of hunting prey their own size would be refined and perfected over millions of years. The oceans were about to witness an arms race that would produce some of the most terrifying predators in Earth's history, creatures that would make even Thalatorchan look like a practice run for the real monsters to come. Chapter 4. The Tyrant Lizards of the Sea Picture, the final chapter of the Age of Dinosaurs. 70 million years ago, on land, Tyrannosaurus rex stalks through primeval forests. But in the warm, shallow seas that cover much of North America and Europe, something even more terrifying rules the waves. Mosasaurus was a type of derived mosasaur, or a late-coming member with advanced evolutionary traits, such as a fully aquatic lifestyle. As such, it had a streamlined body, an elongated tail ending with a downturn supporting a two-lobed fin, and two pairs of flippers. During the last 20 million years of the Cretaceous period, Turonian Maastrichtian ages, with the extinction of the ichthyosaurs and pliosaurs, mosasaurids became the dominant marine predators. They themselves became extinct as a result of the KPG event at the end of the Cretaceous period, about 66 million years ago. But for those 20 million years, they ruled with an iron fist, or rather, iron jaw. Mosasaurus hoffmanni, the largest known species, reached up to 17 meters, 56 feet, making it larger than a modern sperm whale and infinitely more dangerous when the French Revolutionary Forces occupied Maastricht in 1794. The carefully hidden fossil was uncovered after a reward, it is said, of 600 bottles of wine, and transported to Paris. This fossil, a massive skull with jaws that could swallow a horse, would revolutionize our understanding of extinct life, after it had been earlier interpreted as a fish, a crocodile, and a sperm whale. The first to understand its lizard affinities was the Dutch scientist Adrian Gilles Camper in 1799. In 1808, Georges Cuvier confirmed this conclusion, although Le Grand Animal Fossile de Maastricht was not actually named Mosasaurus, Muse reptile, until 1822. What they had discovered was proof that lizards, humble terrestrial lizards, had somehow evolved into sea monsters that dwarfed anything alive today. The mosasaurs, on the other hand, differ from the other groups of Mesozoic-age marine reptiles in that they're part of the reptilian order known as Squamata, which comprises lizards and snakes. They were the last major group of marine reptiles to make an appearance around 94 million years ago, and while they weren't quite as stocky as the Thalassophonian pliosaurs, they did grow longer, the largest, Mosasaurus hoffmanni, reaching lengths of up to 17 m. Think about the evolutionary journey this represents. These creatures didn't evolve in the ocean like sharks or transition gradually like ichthyosaurs. They started as small, coastal lizards, and underwent one of the most dramatic evolutionary transformations in Earth's history. Mosasaurs were so well adapted to this environment that they most likely gave birth to live young, rather than returning to the shore to lay eggs as sea turtles do. They had completely severed their ties to land, becoming as aquatic as any whale or dolphin. The strong jaws of mosasaurs were lined with sharp teeth, enabling them to hunt a wide variety of prey, including fish, sharks, cephalopods, and even other marine reptiles. Their anatomy suggests they were fast and agile swimmers, capable of ambushing or pursuing their prey. But Mosasaurus was more than just another marine predator. Mosasaurus hoffmanni was the apex predator of the late Cretaceous oceans, reaching 11 meters, 36 feet in length and 3.8 metric tons, 4.2 short tons. In body mass, the numbers tell the story. Imagine a predator the length of a school bus, weighing as much as 3 cars, moving through the water with the speed and agility of a dolphin. The tail structure of Mosasaurus is similar to relatives like Prognathodon, in which soft tissue evidence for a 2-lobed tail is known. While in the past derived mosasaurs were depicted as akin to giant flippered sea snakes, it is now understood that they were more similar in build to other large marine vertebrates such as ichthyosaurs, marine crocodilomorphs, and archaeocet whales through convergent evolution. This convergent evolution reveals something profound. There are only so many ways to build a perfect marine predator. The tail vertebrae gradually shorten around the center of the tail and lengthen behind the center, suggesting rigidness around the tail center and excellent flexibility behind it. The forelimbs of Mosasaurus are wide and robust. The scapula and humerus are fan-shaped and wider than tall. Every aspect of mosasaur anatomy was refined for one purpose: being the most efficient killer in the ocean. Virtually all forms were active predators of fish and ammonites. A few, such as globines, have blunt, spherical teeth specialized for crushing mollusk shells. The smaller genera, such as Plodocarpus and Dallosaurus, which were about 1 to 6 meters, 3¼ to 19 2/3 feet long, probably fed on fish and other small prey. The diversity of mosasaurs was staggering. The smallest known mosasaur was Dallosaurus toneri, which was less than 1 meter, 3.3 feet long. Larger mosasaurs more typical, with many species growing longer than 4 meters, 13 feet. They had specialized into every conceivable aquatic niche. This wasn't just one type of sea monster. This was an entire empire of aquatic predators, from small, fast interceptors to massive, whale-sized apex predators. After ichthyosaurs and pliosaurs faced extinction in the early late Cretaceous, mosasaurs took over and ruled the oceans up until 66 million years ago. Mosasaurus had a global distribution, and fossils of the shark have been found in many places around the world, bordering all oceans of the Neogen. Mosasaurus fossils have been found in North and South America, Europe, Africa, Western Asia, and Antarctica. This distribution encompassed a wide range of oceanic climates, including tropical, subtropical, temperate, and subpolar. From an ecological standpoint, Mosasaurus probably had a profound impact on the structuring of marine ecosystems. Its arrival in some locations, such as the Western Interior Seaway in North America, coincides with a complete turnover of faunal assemblages and diversity. When mosasaurs arrived in a region, everything changed. They were ecosystem engineers, apex predators whose very presence reshaped entire marine communities. Paleontologists believe its diet would have included virtually any animal. It likely preyed on bony fish, sharks, cephalopods, birds, and other marine reptiles, including sea turtles and other mosaurs with a head like that of a crocodile. lined with hundreds of razor-sharp teeth which could tear through well-armored skin. Mosasaurus was a colossal predator of the Cretaceous period. It is believed that this creature would wait in the dark to charge at marine mammals that came up for air. This hunting strategy reveals the intelligence behind the brute force. Mosasaurs weren't just mindless eating machines. They were sophisticated predators capable of complex behaviors. The massive and oval jaws of this marine dinosaur make it look like a crocodile. They are often called the sea lions of the primitive ocean. In 2011, collagen protein was recovered from a prognathodon humerus, dated to the Cretaceous. This remarkable preservation has allowed scientists to study not just the bones, but the actual proteins that made up these creatures' bodies. More recently, a fossil of Plotocarpus tympaniticus has been found that preserved not only skin impressions, but also internal organs. Several reddish areas in the fossil may represent the heart, lungs, and kidneys. The trachea is also preserved, along with part of what may be the retina in the eye. The placement of the kidneys is farther forward in the abdomen than it is in monitor lizards, and is more similar to those of cetaceans. As in cetaceans, the bronchi leading to the lungs run parallel to each other instead of splitting apart from one another as in monitors and other terrestrial reptiles. In mosasaurs, these features may be internal adaptations to fully marine lifestyles. These anatomical adaptations reveal creatures perfectly designed for ocean life. They hadn't just adapted to the ocean, they had been re-engineered by evolution to dominate it. However, the discovery of several specimens of juvenile and neonate-sized mosasaurs, unearthed more than a century ago, indicate that mosasaurs gave birth to live young, and that they spent their early years of life out in the open ocean, not in sheltered nurseries or areas such as shallow water as previously believed. This commitment to ocean life would ultimately be their downfall. When the asteroid struck at the end of the Cretaceous, the marine ecosystems that supported the mosasaur empire collapsed almost instantly. Unlike land animals that could shelter and scavenge, the specialized ocean predators had nowhere to hide. The mosasaur empire represents the pinnacle of marine reptile evolution. For 160 million years, various marine reptiles had ruled the oceans. But the mosasaurs perfected the formula. They were faster than pliosaurs, more sophisticated than ichthyosaurs, and more diverse than any marine predator group before or since. Mosasaurs are considered one of the top marine predators of their time, and their widespread fossil distribution highlights their success and adaptability in ancient marine ecosystems. They proved that intelligence, speed, and adaptability could triumph over brute force and armor. But even as the mosasaur empire reached its peak, other predators were evolving in parallel, creatures that would challenge even the mighty Mosasaurus for oceanic supremacy. In the depths of the same Cretaceous seas, massive marine reptiles with different evolutionary strategies were preparing for their own bid for ocean domination. The age of the pliosaurs was overlapping with the age of the mosasaurs, setting up one of the most epic predatory competitions in Earth's history. Chapter 5. The Short-necked Titans. The world's oceans were home to many monstrous marine reptiles during the Mesozoic, and chief amongst them were the pliosaurs. Computer-generated reconstructions show us creatures that seem impossible. Marine reptiles with heads comprising nearly a quarter of their total body length, jaws that could crush a small car, and bite forces that made Tyrannosaurus rex look like a house cat. For more than 80 million years, the pliosaurs were the apex predators of the world's oceans, feasting on all manner of prey from large fish to other marine reptiles, including their close cousins, the plesiosaurs. The largest thalassophonian pliosaurs, such as Kronosaurus, Pliosaurus macromeris, and the unnamed species described above, are thought to have hunted by ambushing their prey from below. using their powerful jaws and incredibly sharp teeth to dismember prey. Oftentimes in a single bite, these weren't just big marine reptiles. They were evolution's answer to a simple question. What would happen if you took the head of T-Rex and attached it to the body of a whale? The Thalassophonian pliosaurs looked like a cross between a crocodile and a whale, with short necks, huge heads, large, paddle-shaped flippers, and powerful, hydrodynamic bodies. They were the largest members of Plisosauria, reaching lengths of more than 11 meters in the case of Kronosaurus and Plesiosaurus macromeris. But calling them large doesn't capture the sheer terror these creatures represented. In general, plesiosaurians varied in adult length from between 1.5 meters, 4.9 feet, to about 15 meters, 49 feet. The group thus contains some of the largest marine apex predators in the fossil record, roughly equaling the longest ichthyosaurs, mosasaurids, sharks, and toothed whales in size. Think about that for a moment. Pliosaurs were competitive in size, with the largest predators in Earth's history, including modern sperm whales and the extinct megalodon shark. But unlike those creatures, pliosaurs combined massive size with the intelligence and agility of reptiles in the middle of the Jurassic. Very large Pliosauridae evolved. These were characterized by a large head and a short neck, such as Liopleurodon and Cymolestes. These forms had skulls up to 3 meters, 10 feet, long and reached a length of up to 17 meters, 56 feet, and a weight of 10 tons. A 3-meter skull. Let that sink in. That's longer than a small car, filled with teeth the size of bananas. Some plesiosaurian remains, such as a 2.875-meter long, 9.43 feet, set of highly reconstructed and fragmentary lower jaws preserved in the Oxford University Museum and referable to Pliosaurus. Rossicus indicated a length of 17 meters, 56 feet. However, it was recently argued that its size can't be determined, due to their being poorly reconstructed, and a length of 12.7 meters, 42 feet, or less is more likely. In 2023, the length of its mandible was estimated to be 2.6 meters, suggesting a length of 11.8 meters, 39 feet, and a weight of over 20 tons, 20 long tons, 22 short tons. Even with conservative estimates, we're talking about predators the size of modern sperm whales, but built for active hunting rather than suction feeding. The pliosaurids had large, conical teeth and were the dominant marine carnivores of their time. But these weren't just big teeth, they were precision instruments, designed for specific types of killing. Kronosaurus is one of the more famous fossil discoveries to come from Australia, and as a huge short-necked pliosaur, Kronosaurus would have been an apex predator of the waters it swam in. The teeth of Kronosaurus are conical and up to 30 centimeters long, although most of that was root with up to 12 centimeters making up the exposed crown. 12 centimeters of exposed crown means teeth nearly 5 inches long, designed to punch through the armor and bones of other marine reptiles. Interestingly, the teeth of Kronosaurus are quite different to other pliosaurs in that they are not serrated and do not have 3 facets. The teeth may suggest that despite its large size, Kronosaurus may have seized smaller to medium-sized prey, which could then be manipulated to be swallowed. The only way that Kronosaurus could have fed from larger prey would be to clamp on with its jaws and then use brute strength from its body to twist or rolling. Either way, it seems that Kronosaurus may have eaten in a similar manner to a crocodile. But imagine a crocodile the size of a sperm whale, with flippers instead of legs, performing death rolls in the open ocean. The physics of such an attack would have been devastating. The combination of massive body weight, powerful flippers for leverage, and jaws that could exert tremendous force would have made pliosaur attacks unstoppable. Pliosaurus funki, a pliosaur, Species discovered in the Arctic islands of Svalbard in 2009 and previously known as Predator X may have had the highest bite force of any creature ever. The fascinatingly codenamed Predator X is technically a pliosaur subspecies called Pliosaurus funki, but its physical might and the initial mystery surrounding its discovery earn this terrifying marine hunter its own entry. Fossils of this 150-million-year-old creature were first discovered in 2006, and it was immediately clear that it was different from your average pliosaur. But it took until 2012 to figure out that the so-called Predator X was a whole previously undiscovered species. The animal would have been so massive that I think it would have been able to prey effectively on anything that was unfortunate enough to be in its space. He analyzed a particularly well-preserved fossil in an interview with the BBC. I have no doubt that this was sort of like an underwater T-Rex. With their enormous maws, the diet of this large pliosaur species would have included large cephalopods, large fish, and other large reptiles. But it wasn't just what they ate, it was how they ate it. Many believe that the bite of a pliosaur was 4 times stronger than that of a Tyrannosaurus rex. Computer models suggest that Predator X could have had a bite force of around 33,000 pounds per square inch psi. To put that in perspective, a great white shark has a bite force of about 4,000 psi, and T-Rex maxed out at around 12,800 psi. Predator X wasn't just biting, it was crushing reality itself. With a bite force of 33,000 psi, there was literally nothing in the Jurassic oceans that could withstand its jaws. This water dinosaur was Jurassic apex predator. Liopleurodon wielded a skull and jaws comprising 1/5 of its length, armed with 20-centimeter teeth for crushing prey. 4 powerful flippers provided explosive acceleration, while directional nostrils detected blood trails from afar, akin to modern sharks. Despite BBC's infamous 25-meter myth, the largest confirmed specimen, L. ferox, measured 6.39 meters, with a 1.5-meter skull hinting at rare giants up to 7.5 meters. But don't let the smaller size fool you. Liopleurodon was built for a specific type of terror. Some anatomical studies have found that Liopleurodon was likely a very fast and agile swimmer, built for ambushing its prey from below. Like modern great whites, Liopleurodon probably used the element of surprise, launching itself from the depths to strike unsuspecting prey at the surface. Pliosaurs were a terrifying aspect of life in the ocean from 200 to 65.5 million years ago. A group of monsters that varied greatly in size. They were mighty predators that enjoyed the combined advantage of strength, speed, and a maw full of sharp, ridged teeth that were custom designed for repeated bite attacks. But what made pliosaurs truly terrifying wasn't just their physical capabilities, it was their intelligence. Of the senses, sight and smell were important, hearing less so. Elasmosaurids have lost the stapes completely. It has been suggested that with some groups the skull housed electrosensitive organs. These were sophisticated predators with advanced sensory systems. They could track prey through murky water using electrical fields, spot potential targets from great distances, and coordinate complex hunting strategies. From the parental care indicated by the large size of the young, it can be deduced that social behavior in general was relatively complex. It is not known whether plesiosaurs hunted in packs. Their relative brain size seems to be typical for reptiles. The possibility of pack hunting giant marine reptiles is a chilling thought. Imagine encountering not one Predator X, but a coordinated group of them working together to bring down prey, even larger than themselves. In 2012, a mandible of Pliosaurus was described with a jaw joint clearly afflicted by arthritis, a typical sign of senescence. Even these ultimate predators aged, their joints wearing down from decades of crushing prey with forces that could shatter stone. Some plesiosaur fossils show pathologies, the result of illness or old age. These weren't just killing machines, they were long-lived animals that survived in the ocean for decades, accumulating injuries and experience that made older individuals even more dangerous. Masser also tried to compare the speeds of plesiosaurs with those of the two other main sea reptile groups, the Ichthyosauria and the Mosasauridae. She concluded that plesiosaurs were about 20% slower than advanced ichthyosaurs, which employed a very effective tuniform movement, oscillating just the tail, but 5% faster than mosasaurids, while the short-necked plesiosauromorphs, for example Liopleurodon, may have been fast swimmers. The long-necked plesiosauromorphs were built more for maneuverability than for speed, slowed by a strong skin friction, yet capable of a fast rolling movement. This trade-off between speed and maneuverability meant that pliosaurs excelled in close-quarters combat. They might not catch everything they chased, but once they got within striking distance, nothing could escape their jaws. It's no surprise then that these creatures were the top dogs of their day, to the point that the biggest threat to a pliosaur was another pliosaur. The pliosaurs represent the ultimate expression of the bigger is better philosophy in marine predator evolution. Pliosaurs possessed powerful jaws and large teeth, and they used 4 large fins to swim through Mesozoic seas. But more than that, they represented a perfect balance of size, power, intelligence, and hunting strategy that wouldn't be seen again until the rise of modern whales. As dominant as the pliosaurs were, they faced competition from some of the most bizarre and massive sharks ever to prowl the oceans. While pliosaurs perfected the art of crushing their prey, these ancient sharks were developing their own terrifying innovations: teeth the size of your hand and bodies that dwarf modern great whites. The ultimate predator showdown was about to begin. Chapter 6. The megashark dynasty. Cocoricles megalodon was once the most fearsome predator to reign the seas. This ancient shark lived roughly 23 to 3.6 million years ago in nearly every corner of the ocean, roughly up to 3 times the length of a modern-day great white shark. It is the largest shark to have ever lived. But numbers alone cannot capture the sheer terror that megalodon represented. Picture a great white shark, already one of the ocean's most feared predators. Now imagine that shark growing until it's the size of a school bus, its mouth wide enough to swallow a small car, its teeth the size of your hand. It had a powerful bite with a jaw full of teeth as large as an adult human's hand. They likely could tear chunks of flesh from even the largest whales of the time. For over 20 million years, megalodon ruled the oceans with an iron jaw. This wasn't just the largest shark that ever lived. It was the ultimate expression of predatory evolution, a creature so perfectly designed for killing that it redefined what it meant to be an apex predator. The largest were roughly 60 feet in length and attained perhaps up to 50 tons, the size and weight of a railroad car. Female megalodons were on average larger, at about 44 to 56 feet, 13 to 17 meters, and males were about 34 to 47 feet, 10 to 14 meters. To put this in perspective, a modern great white shark, one of today's most feared predators, maxes out at about 20 feet and 5,000 pounds. Megalodon was 3 times longer and 10 times heavier. Millions of years ago, monstrously sized sharks named megalodons dominated the ocean. These giants grew larger than modern-day humpback whales, casually snacked on animals like dolphins and seals, had the strongest bite force of any creature to ever exist, yes, including T-Rex. Think about what it would mean to encounter such a creature. Modern great whites are already large enough to breach completely out of the water when attacking seals. A breaching megalodon would have been like watching a freight train launch itself into the air. It preyed upon fish, baleen whales, toothed whales, such as ancestral forms of modern sperm whales, dolphins and killer whales, sirenians, such as dugongs and manatees, and seals. The young likely sought out smaller prey, while adults hunted larger whales. But Megalodon wasn't just a scaled-up great white. Whereas great whites dive straight toward their prey's soft tissue, say, a carelessly exposed underbelly, Megalodon's teeth were suited to biting through tough cartilage, and there's some evidence that it may have first sheared off its victims' fins, rendering it unable to swim away before lunging in for the final kill. This reveals a sophisticated hunting strategy. Rather than going for the quick kill like modern sharks, Megalodon employed a more methodical approach. Disable the prey first, then move in for the kill. It's the difference between a quick stab and prolonged torture. Scientists calculate that a bite from a Megalodon jaw could generate force of up to 40,000 pounds, which would make it the strongest bite in the entire animal kingdom. To understand what this means, consider that a human bite exerts about 162 pounds of force. A lion manages 650 pounds, and even the mighty T-Rex could only generate about 12,800 pounds. Megalodon's bite was more than 3 times stronger than T-Rex. We're used to thinking of the largest species, blue whales, whale sharks, even elephants and diplodocuses, as filter feeders or herbivores, not predators, says the paper's lead author, geoscientist Emma Cast, now based at the University of Cambridge, UK. But Megalodon and the other megatooth sharks were genuinely enormous carnivores that ate other predators. The physics of such a bite force in water would have been devastating. Water doesn't compress, so all that force would have been transmitted directly to the victim. A single bite could have shattered the spine of a whale or crushed the skull of any marine animal. Cast and Sigmund's team discovered clear evidence that Megalodon and its ancestors occupied the highest rung of the prehistoric food chain, called the highest trophic level. So high is their trophic signature that the researchers believe Megalodon must have eaten other predators and predators of predators in a complicated food web. This wasn't just being at the top of the food chain. This was creating an entirely new level above the food chain. If Megalodon existed in the modern ocean, it would thoroughly change humans' interaction with the marine environment, adds senior author Danny Sigmund, professor of geological and geophysical sciences at Princeton. Think about what this means. Modern orcas, the current apex predators of the ocean, hunt in coordinated pods and can take down great white sharks. But even a pod of orcas would have been helpless against a single adult Megalodon, unlike some marine predators of prehistoric times, which were restricted to the coastlines or inland rivers and lakes of certain continents. Megalodon had a truly global distribution, terrorizing whales in warm water oceans all over the world. The Megalodon lived in most regions of the ocean, except near the poles. While juveniles kept to the shores, adults preferred coastal areas, but could move into the open ocean from the coasts of North America to the depths of the Pacific. From European waters to the southern oceans, Megalodon was everywhere. The most northern fossils are found off the coast of Denmark, and the most southern in New Zealand. This global distribution meant that for over 20 million years, no ocean was safe. Helping Megalodon on its way to the top of the food web is cannibalism. There is evidence of cannibalism in both megatooth sharks and other prehistoric marine predators. But Megalodon cannibalism wasn't just occasional. It was systematic. In 2020, Shimada and colleagues suggested large size was instead due to intrauterine cannibalism, where the larger fetus eats the smaller fetus, resulting in progressively larger newborns. Even before birth, Megalodon babies were eating their siblings. The largest and most aggressive survived to be born, already hardened killers from their time in the womb. This intrauterine cannibalism meant that every Megalodon that survived to birth had already proven itself as a predator. They were literally born killers, shaped by violence before they ever saw the ocean. Like the modern-day bull shark, megalodons gave birth in specific nursery habitats that included protected bays and estuaries. These locations provided the shark pups with plenty of fish and a safe environment to grow, away from the larger predators of the open ocean and offshore zones. But despite being fierce predators, a new study published last week in the journal Biology Letters suggests that megalodons were pretty good parents and raised their young in nurseries. This reveals a sophisticated behavioral ecology. Megalodons weren't just mindless eating machines. They were intelligent predators with complex social behaviors. Scientists have discovered megalodon nursery habitats in Panama, Maryland, the Canary Islands, and Florida. These nurseries represent a global network of safe havens, where the ocean's most dangerous predator carefully raised its young. The genus Carcharodonts contains 4 species: C. auriculatus, C. angustidens, C. chubaltensis, and C. megalodon. The evolution of this lineage is characterized by the increase of serrations, the widening of the crown, the development of a more triangular shape, and the disappearance of the lateral cusps. The evolution in tooth morphology reflects a shift in predation tactics from a tearing, grasping bite to a cutting bite, likely reflecting a shift in prey choice from fish to cetaceans. Over millions of years, megalodon evolved specifically to hunt whales, the largest prey available in the ocean. This wasn't just getting bigger randomly. This was targeted evolution, with each generation becoming more specialized for hunting specific types of prey. Megalodon faced a highly competitive environment. Its position at the top of the food chain probably had a significant impact on the structuring of marine communities. But they weren't alone at the top. Megalodon were contemporaneous with whale-eating toothed whales, particularly macroraptorial sperm whales and squalidintidae, which were also probably among the era's apex predators and provided competition for the same prey. The oceans of the Miocene were an arena where multiple apex predators competed for dominance. These considerations, as well as tooth oxygen isotopic data and the need for higher burst swimming speeds and macropredators of endothermic prey than ectothermy, would imply that otodontids, including megalodon, were probably regional endotherms. This means megalodon could regulate its body temperature, giving it a massive advantage over cold-blooded marine reptiles. Regional endothermy allowed for burst speeds necessary to hunt fast-moving whales and provided the stamina for long-distance hunting. Many whale fossils have distinct gashes from megalodon teeth, and sometimes an entire megalodon tooth is found embedded in a whale bone. The fossil record is filled with evidence of megalodon's hunting prowess. An ancient shark left behind a piece of itself when it bit into its prey. These embedded teeth tell stories of titanic battles between the ocean's largest predators and largest prey animals. In some cases, whales survived megalodon attacks, carrying the shark's teeth in their bones like battle scars. With such a large body size, the megalodon required ample prey to fuel its body. Around 2.6 million years ago, around the time when the megalodon disappears from the fossil record, large mammals in the ocean were undergoing significant changes in response to a changing climate. Geological events changed currents and precipitation. Among these were the closure of the Central American Seaway and changes in the Tethys Ocean, contributing to the cooling of the oceans. The stalling of the Gulf Stream prevented nutrient-rich water from reaching major marine ecosystems, which may have negatively affected its food sources. The very success of megalodon became its downfall. When climate change altered ocean currents and temperatures, the massive energy requirements of the world's largest predator became unsustainable. The largest fluctuation of sea levels in the Cenozoic era occurred in the Pleistocene between around 5 million to 12,000 years ago. due to the expansion of glaciers at the poles, which negatively impacted coastal environments and may have contributed to its extinction, along with those of several other marine megafaunal species. Nursery areas are pivotal for the survival of many shark species, in part because they protect juveniles from predation. The loss of warm, shallow nursery areas may have been the final nail in Megalodon's coffin. Even the ocean's ultimate predator was vulnerable to environmental change, but Megalodon wasn't the only massive predator prowling the ancient oceans. In the same waters where these giant sharks hunted whales, other predators were evolving their own approaches to becoming the ocean's apex killer. Some abandoned the shark model entirely, developing into something even more terrifying: predatory whales with teeth longer than railroad spikes and intelligence that made them the orcas of their time, but orcas the size of modern sperm whales and infinitely more dangerous. Chapter 7. The Whale That Ate Whales. The ancient oceans were not only home to monstrous sharks, but also to the formidable Leviathan Melville. This giant predatory whale boasted 14-inch teeth, rivaling the size of those found in Tyrannosaurus Rex. Leviathan's powerful jaws allowed it to hunt large prey, including other whales. But calling Leviathan simply a predatory whale is like calling Megalodon just a big shark. What we're dealing with here is something far more terrifying. A creature that combined the size and power of a sperm whale with the hunting instincts of an orca, armed with the largest functional teeth ever discovered in any animal. When first described, Leviathan was actually named Leviathan after the biblical sea monster. Unfortunately, however, Leviathan had already been used to name a mastodon, so the Hebrew word for Leviathan, Leviathan, is now used to refer to this ancient whale. The species name, L. Melville, is in honor of the author Herman Melville, the man who wrote the world-famous novel Moby Dick. The naming tells the story. This wasn't just any prehistoric whale. This was a creature so massive and so terrifying that scientists immediately thought of biblical sea monsters and literature's most famous whale tale. Leviathan Melville was a giant prehistoric sperm whale whose enormous teeth measured up to 36 centimeters, 14 inches in length. To put this in perspective, T-Rex teeth maxed out at about 8 inches including the root. Leviathan's teeth were nearly twice as long, and these were functional, working teeth designed for processing prey. That it had the largest teeth of any animal, aside from elephants' tusks. Granted, some animals like elephant have modified teeth that form tusks which are even bigger, but they are useless for processing food in the mouth, so in this case, they do not count as the largest. Leviathan also had teeth in both the upper and lower jaws for grasping prey. The modern sperm whale, the closest living analogy to Leviathan, only has teeth on the lower jaw, unlike modern sperm whales, which have teeth only in their lower jaws. Leviathan had teeth in both upper and lower jaws, suggesting it was an active predator. This wasn't a suction feeder like modern sperm whales. This was a precision killer designed to grab, hold, and tear apart massive prey. Because only the skull is known, Leviathan is often compared to the sperm whale, Physeter macrocephalus, when piecing together the rest of the body. This has yielded size estimates of 13.5 meters, which make Leviathan a comparable size to the mega-toothed sharks like Megalodon. Think about this comparison. Leviathan was roughly the same size as Megalodon, but where the shark was all muscle and instinct, the whale brought intelligence to the hunt. The Leviathan Melville wasn't any bigger than the sperm whales of today, but unlike sperm whales, this creature used its massive teeth to chomp down on its prey and trap it within its 10-foot skull. However, Leviathan has also been compared to another prehistoric whale named Zygophyseter, and this resulted in an estimate of 17.5 meters. If accurate, then this would make Leviathan comparable to even Megalodon, the largest shark to ever swim the ocean. In fact, for a time, both Leviathan and Megalodon would have swam in the same oceans. Not only was Leviathan an apex predator like Megalodon, it probably fed upon the same prey animals, which were medium-sized baleen whales. This sets up one of the most epic predatory confrontations in Earth's history. The largest shark that ever lived versus the largest predatory whale that ever lived, competing for the same prey in the same oceans. As reported by Nature, Leviathan may have even competed with Megalodon for dominance, cementing its place as one of the most fearsome marine predators in prehistoric history. Imagine the encounter. A 60-foot shark meets a 60-foot predatory whale, both armed with teeth designed to kill other whales, both accustomed to being the apex predator wherever they went. So, how impressive was Leviathan to warrant such a cool scientific name? Impressive enough to handily beat a Megalodon in a fight if necessary, it turns out. This prehistoric predator could be up to 60 feet long and somewhat resembled a massive sperm whale with a disproportionately huge, 4-foot wide mouth that was full of 14-inch teeth. How Leviathan hunted it's still a matter of debate, but given its large mouth and teeth, it may have used a similar method to kill smaller whales as Megalodon did. This could be approaching from the bottom and slamming into its target from underneath. An associated method could also be trapping the smaller whale's ribcage in its jaws and crushing the ribs to create fatal injuries to the internal organs. But Leviathan had options that Megalodon didn't. Another method could see Leviathan holding down a whale beneath the surface to stop it surfacing for air. This is a strategy that would be potentially risky for Leviathan, as it too would still need to surface for air. This drowning strategy reveals the intelligence behind Leviathan's hunting. While Megalodon relied on bite force and bleeding out its prey, Leviathan could use sophisticated tactics that required understanding of its prey's biology and behavior. The Leviathan Melville also had echolocation abilities, unlike the other marine life during the time, allowing it to survive the murkiest ocean depths. This hyper-carnivorous whale loved to dine on shark species. Echolocation gave Leviathan a massive advantage over every other predator in the ocean. While Megalodon and marine reptiles relied on vision and sensing electrical fields, Leviathan could see with sound, tracking prey through murky water, around corners, and in total darkness. This wasn't just having good hearing. This was having biological sonar more sophisticated than anything humans have developed. Leviathan could map its environment in real time, track multiple prey animals simultaneously, and coordinate complex hunting strategies in ways that no other marine predator could match. With teeth that were 36 centimeters long, Leviathan had the dentition to take down large prey items. In fact, not only were the teeth of Leviathan considerably larger than Megalodon teeth, they are considered to be the largest known teeth for the purpose of eating. But size alone doesn't tell the whole story. Smaller juvenile Leviathan may have preferred proportionately smaller prey items like the smaller cetaceans or even large fish. With such a large body size and specialized dentition, Leviathan was probably capable of hunting prey almost as large as itself. The precision of Leviathan's teeth contrasts sharply with Megalodon's approach, where Megalodon's teeth were designed for cutting and tearing. Leviathans were designed for grabbing and holding. This whale could seize prey and control it, rather than just inflicting damage and hoping for a quick kill. Leviathan's enormous teeth grabbed prey with huge chops, aided by its massive 10-foot-long skull that helped to capture and trap food inside. And with its echolocating abilities, other marine life didn't stand much chance, even in the murkiest depths of the ocean. This wasn't just brute force. This was intelligent application of force. Modern sperm whales are among the most intelligent animals on Earth, with complex social structures, communication systems, and problem-solving abilities. Leviathan likely possessed similar intelligence, but applied it to active predation rather than deep-sea squid hunting. Though no bigger than today's sperm whales, which also rely on suction to carry prey into their open mouths. Leviathan's enormous teeth grabbed prey with huge chops. The comparison to modern sperm whales raises intriguing questions about Leviathan's social behavior. Modern sperm whales are highly social, living in family groups with complex communication systems. If Leviathan retained similar social structures while becoming an active predator, it might have hunted in coordinated groups. Imagine pods of predatory whales the size of school buses working together to hunt other whales. This style of attack has also been implied for the giant shark Megalodon as well as predatory whales such as Leviathan, and suggests that while the predators and prey were different throughout the ages, the actual method of attack was principally the same. Despite the devastating nature of such an impact, such an attack would actually require patience and timing to execute properly, as while the prey was smaller, it was almost certainly more maneuverable than a fully grown Leviathan. This makes attacks in the same depth plane unlikely because despite its speed, prey would have likely seen the attack coming and taken avoiding action. This is why it makes the most sense for a marine predator to approach its target from below, as not only can it home in unseen, other sensory adaptations, such as the pressure and electroreceptors of fish, tend to work in sideways directions, and any scent from the predator would also drift sideways in the ocean currents, not up. This prehistoric marine predator likely hunted large prey, including other marine mammals such as seals and smaller whales. Its massive size and formidable dentition made it one of the top predators in the Miocene oceans, similar to the modern orca in terms of ecological role. But unlike modern orcas, which are relatively small and hunt in coordinated pods, Leviathan was a solitary giant capable of taking down prey through individual effort. This created a very different type of ocean ecosystem, one where even large whales weren't safe from individual predators. The rise of Leviathan represents a unique moment in evolutionary history when mammals developed their own answer to the FUD mega sharks. While cartilaginous fish had dominated marine predation for hundreds of millions of years, mammals proved they could play the same game and potentially play it better. The intelligence factor cannot be overstated. Where previous marine predators relied primarily on size, strength, and instinct, Leviathan brought mammalian intelligence to oceanic predation. This combination of size, strength, and intelligence created what may have been the most formidable marine predator in Earth's history. As terrifying as individual giant predators were, the oceans were about to witness something even more frightening: the rise of marine reptiles that combined massive size with advanced social behaviors. These weren't just big predators. They were intelligent hunters that worked together, creating the ocean's first predatory societies. The age of coordinated terror was about to begin. Chapter 8. The pack hunters of the abyss, one species that did survive. Originally, a land creature that adapted to live in the sea, became the ichthyosaur. Ichthyosaur means fish lizard in Greek. They were fish-like in appearance, with a tail and paddle-style appendages used to propel and steer themselves. But this simple description masks one of the most remarkable transformations in evolutionary history. These weren't just reptiles that learned to swim. They underwent one of the most complete evolutionary makeovers ever recorded, becoming living torpedoes perfectly designed for oceanic predation. Though generally about 10 feet in length, certain fossils indicate that some ichthyosaurs could be over 40 feet. Some lived and foraged in coastal waters at the edge of continents, while others swam in the open ocean, far from land. Like whales and porpoises today, they gave birth to their young at sea. What makes ichthyosaurs truly terrifying isn't just their size or speed. It's their intelligence and potential for coordinated hunting. Recent discoveries suggest these weren't solitary predators, but sophisticated pack hunters that ruled the oceans through teamwork and strategy. The ichthyosaur is a marine reptile that reigned the seas during the Mesozoic era, the age of dinosaurs. The ichthyosaur had a protruding bill, filled with teeth that allowed for quick jabs at fish. The plesiosaur swam with 4 paddle-like flippers, unlike anything that exists in today's seas. But the most striking similarity between today's top predators and the top predators of ancient seas is the tail fluke. Time and time again, creatures have evolved a crescent moon-shaped tail. Not only is this visible in whales, dolphins, and sharks, it is also the case for mosasaurs and ichthyosaurs. This convergent evolution reveals something profound. There are optimal designs for oceanic predation, and ichthyosaurs discovered them independently. The resemblance of ichthyosaurs to living fish and dolphins is an example of convergent evolution, the phenomenon of unrelated animals developing similar characteristics. When first discovered in the early 1800s, scientists thought all ichthyosaurs had a straight, eel-like tail. Indeed, many of the early ichthyosaurs had a primitive, elongate tail, but as ichthyosaurs evolved to be more efficient swimmers, their tails were integral to that transition. It wasn't until the 1890s that a well-preserved skeleton of a more evolved ichthyosaur was found with a proper outline of its body. Bacteria had eaten away at the decomposing body, leaving behind a shadow of the lizard shape in the surrounding rock. This revealed a dorsal fin and a crescent moontail. This discovery revolutionized our understanding of ichthyosaur capabilities. Marine reptiles, like sharks, beat their tailies from side to side, while whales and dolphins beat their tailies up and down. The efficiency of this design allowed ichthyosaurs to achieve remarkable speeds. Masser concluded that plesiosaurs were about 20% slower than advanced ichthyosaurs, which employed a very effective tuniform movement, oscillating just the tail. This made ichthyosaurs the speed champions of the Mesozoic seas. A deep-diving Jurassic ichthyosaur, Ophthalmosaurus, reached 6 meters, with eyes proportionally larger than any known marine creature, supported by bony scleral rings to withstand crushing depths. Fossils reveal decompression sickness, the bends, evidence of routine dives beyond 500 meters to hunt squid in lightless zones, evading predators like Liopl, Odon. Think about what this means. Ichthyosaurs were making dives deeper than modern sperm whales in oceans filled with massive predators like Lioploirodon and other pliosaurs. They weren't just fast swimmers, they were three-dimensional hunters, capable of utilizing the entire water column. Its disc-shaped vertebrae minimized gas buildup, enabling 20-minute submerged hunts. This level of anatomical specialization reveals creatures that had completely mastered their aquatic environment. They could hunt in the depths where no other air-breathing predator could follow. The name ichthyosaurs means fish lizard. Size ranged from under 1 meter, 3 feet, to over 20 meters, 66 feet, in length, depending on the species. But it's the largest species that truly capture the imagination. Several specimens, but only the bony head and jaws, are known. Shastasaurus Pachyvicus, the largest ichthyosaur, reached lengths of 21 meters. This made it larger than most pliosaurs, competitive with the biggest mosasaurs, and approaching the size of modern blue whales. But unlike blue whales, which are filter feeders, Shastasaurus was a predator. Imagine a creature the length of 2 school buses, shaped like a dolphin, with the speed of a tuna and the hunting instincts of a shark. This wasn't just big. This was the ocean's ultimate predator. Several specimens, but only the bony head and jaws are known. Diet: specialist of soft-bodied cephalopods like fish. The largest ichthyosaurs weren't generalist predators. They were specialists that had evolved to hunt specific types of prey with incredible efficiency. Ichthyosaurs were likely top predators, feeding on fish, squid, and other marine organisms. They are known for giving live birth, as evidenced by fossilized remains of pregnant individuals. But their specialization went far beyond simple predation. The fossil record reveals ichthyosaurs with stomach contents preserved, showing they targeted everything from small fish to large marine reptiles. Some species developed longer snouts for catching fast fish, while others had broader jaws for tackling larger prey. Ichthyosaurs weren't much use on land and would be helpless if stranded ashore. But in the water, they were perhaps the most sophisticated predators of their time. Their large brains relative to body size suggest intelligence comparable to modern dolphins. Live birth is confirmed by over 50 pregnant specimens, each carrying 2 to 11 pups, showcasing viviparity as a key adaptation. This reproductive strategy allowed Ophthalmosaurus to thrive without land, dominating deep niches while other ichthyosaurs hunted near the surface. The discovery of pregnant ichthyosaurs tells us something crucial. These weren't just big predators. They were carrying parents. Like modern whales and dolphins, they likely had complex social structures and taught their young sophisticated hunting techniques. Recent fossil discoveries suggest something even more remarkable: coordinated hunting behavior. Fossil evidence shows that some ichthyosaur species may have hunted in groups, working together to bring down prey much larger than any individual could handle alone. Modern dolphins demonstrate how intelligent marine mammals can coordinate complex hunting strategies. Groups of dolphins will work together to herd fish, create mud nets, or even beach themselves temporarily to catch prey. If ichthyosaurs possess similar intelligence and social structures, they could have employed equally sophisticated tactics. But body shape isn't the only trait sea lizards and top predators of today have in common. Recently, scientists discovered that some lizards were able to do this to some extent too, at certain points in time. To understand ancient sea lizard metabolism, scientists turned to clues hidden in the teeth of ichthyosaurs, plesiosaurs, and mosasaurs. Both ichthyosaurs and plesiosaurs were found to have a body temperature similar to that of today's whales, between 95 to 102 degrees Fahrenheit, 35 to 39 degrees Celsius. This endothermic capability gave ichthyosaurs a massive advantage over cold-blooded marine reptiles. Warm-bloodedness enabled sustained high-speed swimming, allowed for rapid pursuit of prey, and provided the energy necessary for complex behaviors like coordinated hunting. Scientists believe both the ancient reptiles and the sharks evolved in such a way to demands of being a powerful predator, for traveling long distances or for quick bursts of speed. Ophthalmosaurus reached 6 meters, with eyes proportionally larger than any known marine creature, supported by bony scleral rings to withstand crushing depths. These weren't just big eyes, they were sophisticated optical instruments. The largest ichthyosaur eyes discovered were over 10 inches in diameter, larger than dinner plates. These massive eyes could gather light in the depths where no other predator could see, giving ichthyosaurs a decisive advantage in low-light hunting. The bony rings around the eyes served as internal pressure suits, allowing these predators to dive to crushing depths while maintaining perfect vision. They could literally see in places where other predators were blind. Their blend of crocodilian heritage and ichthyic adaptations underscores Mesozoic ocean's ecological complexity, bridging niches between fish eaters and the reptilian leviathans to come. Ichthyosaurs mastered both temporal and spatial hunting strategies. They could hunt in the shallows during the day, dive to the depths at night, migrate across entire ocean basins following prey, and potentially coordinate attacks across multiple depth zones. No other marine predator group achieved such complete mastery of their environment. Evolution can act in what seems like mysterious ways, shaping unrelated creatures to appear and operate in similar manners despite living millions of years apart. So, as you envision massive sea lizards roaming ancient seas, just think about the creatures of today. You may be surprised by how close your vision is to reality, but ichthyosaurs weren't just copying modern designs, they were pioneering them. They achieved many adaptations millions of years before mammals independently evolved the same solutions. Ichthyosaurs represent the pinnacle of reptilian adaptation to marine life. They proved that with enough evolutionary time and pressure, reptiles could match or exceed the capabilities of any marine predator. Their 160 million year reign in the oceans was a testament to the power of specialized evolution. More importantly, they demonstrate that intelligence and coordination can be just as important as size and strength in oceanic predation. The most successful marine predators aren't necessarily the biggest. They're the smartest and most adaptable. As impressive as individual predators and even coordinated hunters were, the oceans were about to witness something unprecedented. The rise of creatures so perfectly adapted to marine killing that they would make all previous predators look like practice runs. The ultimate oceanic killers were about to emerge, predators so efficient that they would redefine what it meant to rule the seas. Chapter 9. The Ultimate Ocean Killers. What do you get when you take 500 million years of evolutionary experimentation, countless extinctions and survivals, and the accumulated wisdom of nature's most successful predatory designs? You get the ultimate ocean killers, creatures so perfectly adapted to marine predation that they represent the absolute peak of what evolution can achieve in an aquatic environment. But these weren't just the biggest or strongest predators. These were the smartest, most efficient, most adaptable killers the ocean has ever seen. They combine the size of megalodons, the intelligence of dolphins, the speed of ichthyosaurs, and hunting strategies so sophisticated that they still challenge our understanding of animal behavior. This is the story of evolution's masterpieces, the predators that didn't just dominate their time periods, but achieved a level of perfection in oceanic killing that has never been matched. They were the apex of apex predators, the ultimate expression of hundreds of millions of years of predatory evolution. During the late Jurassic period, around 150 million years ago, something extraordinary was swimming in the oceans. A fully marine crocodile called Dacosaurus. But this wasn't just a crocodile that learned to swim. This was a crocodile that had undergone complete oceanic transformation. With its powerful jaws, Dacosaurus was probably a top predator in its oceanic environment, hunting fish and other marine reptiles. Its fearsome appearance has earned it the nickname Godzilla. But the nickname doesn't capture the sophistication of this predator. Dacosaurus had evolved a vertical tail fin like a shark, flippers instead of legs, and a skull designed for high-speed aquatic pursuit. It retained the crushing bite force of crocodiles while gaining the speed and maneuverability of marine predators. This was evolution's attempt to create the perfect fusion of terrestrial and aquatic killing power. Dunkleosteus had no equal during its reign. Its bite force was similar to that of the T-Rex and greater than that of saltwater crocodile. But we've already explored this armored nightmare. What makes it worthy of inclusion among evolution's ultimate killers isn't just its individual capabilities, it's what it represented. Dunkleosteus was evolution's first attempt at creating an unstoppable marine predator. Everything that came after, every refinement, every innovation, every step forward in predatory evolution was built on the foundation that Dunkleosteus established. It proved that armor, speed, and crushing force could combine to create OCEANIC. Dominance thought the bite force was almost 2 tons. Some scientists estimate that it was over 3 tons. This would mean that the bite force was similar to that of the T-Rex, and greater than that of modern saltwater crocodiles. But unlike T-Rex, Dunkleosteus ruled an environment with no escape routes, the three-dimensional battlefield of the ocean. As we've seen, ichthyosaurs were remarkable predators. But some species took predatory sophistication to levels that wouldn't be seen again until the rise of modern cetaceans. These advanced ichthyosaurs combined massive size, incredible speed, deep diving capability, and potentially complex social behaviors. The most advanced ichthyosaurs possessed brains proportionally larger than most modern reptiles, approaching the brain-to-body ratio seen in intelligent mammals. They developed sophisticated echolocation abilities, complex hunting strategies, and possibly even cultural transmission of knowledge between generations. These creatures represent the first time in Earth's history that marine predators combined physical supremacy with genuine intelligence. They were the ocean's first thinking killers, predators that could plan, coordinate, and adapt their strategies in real time. Several species pushed the boundaries of what was physically possible for marine predators. Shastasaurus, at 21 meters, was competitive with modern blue whales in size, but retained predatory capabilities. Megalodon at 18 meters was the largest predatory shark ever. Leviathan at 17 meters was the largest predatory whale ever. These weren't just scaled-up versions of smaller predators. Each represented the culmination of different evolutionary strategies taken to their absolute limits. They proved that in the ocean, there's almost no upper limit to how large a predator can become as long as there's prey large enough to sustain them. But size alone doesn't make the ultimate predator. What made these giants truly terrifying was that they combined maximum size with maximum efficiency. They weren't clumsy giants. They were precision instruments of oceanic destruction scaled up to impossible proportions. The most successful marine predators didn't just excel in one area. They achieved excellence across multiple dimensions of predatory capability. Consider what the ultimate ocean killer would need. Maximum bite force to crush through any armor or bone structure. Exceptional speed to catch even the fastest prey. Advanced intelligence to outthink other intelligent predators. And prey. Perfect hydrodynamics to move efficiently through water. Sophisticated sensory systems to hunt in any conditions. Social coordination to take down prey larger than themselves. Global range to exploit resources across entire ocean basins. Environmental adaptability to survive changing conditions. The most remarkable thing about prehistoric oceans is that different species achieve perfection in different combinations of these traits. No single species achieved maximum capability in all areas, but several came close enough to dominate their eras completely. Some predators achieved ultimate status through sensory supremacy rather than size or strength. The electroreception abilities of ancient sharks allowed them to detect prey in complete darkness or murky water. The echolocation of predatory whales gave them three-dimensional mapping capabilities that no other predator could match. The massive eyes of deep-diving ichthyosaurs, some over 10 inches in diameter, provided vision capabilities that allowed hunting in the abyssal depths where no other air-breathing predator could function. These weren't just big eyes. They were biological telescopes capable of gathering light in environments where other predators were effectively blind. Perhaps the most terrifying aspect of the ultimate ocean killers wasn't their physical capabilities, but their behavioral sophistication. Evidence suggests that some species developed hunting strategies that wouldn't look out of place in modern nature documentaries. Coordinated pack hunting, where multiple predators work together to bring down prey much larger than any individual could handle. Ambush predation from the depths, using the three-dimensional nature of the ocean to achieve complete surprise. Tool use, where predators used environmental features to trap or disorient prey. Some species may have even developed protocultural behaviors, passing successful hunting techniques from parents to offspring and between pod members. This represented the birth of learned predatory behavior in marine environments. The ultimate ocean killers weren't just successful predators. They were evolutionary accelerators that forced rapid adaptation in everything around them. Their very existence drove an arms race that pushed all marine life toward greater speed, intelligence, armor, or defensive strategies. When a megalodon entered an ecosystem, everything else had to evolve or die. Prey animals developed new escape strategies. Other predators evolved new hunting techniques, and entire food webs restructured themselves around these apex killers. This ecological pressure created feedback loops that drove increasingly sophisticated predator-prey relationships, ultimately producing marine ecosystems of unprecedented complexity and lethality. What made some predators truly ultimate wasn't just their dominance during peak times, but their ability to survive mass extinctions that wiped out their competitors. The species that survived multiple extinction events accumulated adaptations and survival strategies that made them increasingly formidable. These extinction survivors had seen it all: climate change, ocean chemistry alterations, sea level fluctuations, asteroid impacts, and volcanic apocalypses. Each survival event taught them, through natural selection, new lessons about adaptability and resilience. By the time they emerged from each extinction, they were more efficient, more adaptable, and more deadly than before. They were the ocean's ultimate stress-tested killing machines. Today's oceans are haunted by the ghosts of these ultimate predators. Great white sharks, orcas, and sperm whales represent evolutionary lineages that learned from and built upon the designs pioneered by prehistoric ocean killers. Modern orcas, for instance, combine intelligence, social coordination, and specialized hunting techniques that echo the strategies of advanced ichthyosaurs. Great whites employ ambush tactics reminiscent of megalodon and pliosaurs. Deep-diving sperm whales use sensory capabilities pioneered by ancient marine reptiles. But here's what's truly chilling. Even our most impressive modern marine predators are pale shadows of what once ruled the oceans. The ultimate ocean killers of the past achieved combinations of size, intelligence, and lethality that no modern predator can match. The ultimate ocean killers emerged when multiple factors aligned perfectly: abundant prey, optimal ocean conditions, evolutionary pressure, and ecological opportunity. They represent what happens when evolution has unlimited time, resources, and selective pressure to perfect the art of oceanic predation. These weren't accidents of evolution. They were the inevitable result of hundreds of millions of years of predatory refinement. Every failed experiment, every extinction, every survival contributed to the knowledge base that eventually produced the ultimate killers. The study of ultimate ocean killers reveals that evolution doesn't just create successful predators, it creates perfect predators. Given enough time and pressure, natural selection will push predatory capability to theoretical limits. These ultimate killers also demonstrate that intelligence and physical capability aren't mutually exclusive. The most successful predators combine both, creating creatures that were not just powerful, but smart about how they used that power. But even ultimate predators face ultimate challenges. Climate change, ocean chemistry shifts, and ecosystem collapse can bring down even the most perfect killing machines. As we'll see, the very success of these ultimate predators often contained the seeds of their own destruction, setting up the conditions for their eventual downfall and replacement by new evolutionary experiments. Chapter 10. The Great Dying. The year is 252 million years ago. The most successful marine predators in Earth's history, creatures that have ruled the oceans for tens of millions of years, are about to face their ultimate enemy. Not another predator, not a competitor, but something far more terrifying. A planet-wide catastrophe that will test whether even evolution's most perfect killing machines can survive when the ocean itself becomes their enemy. This is the story of the Permian Triassic extinction, the great dying that killed up to 96% of all marine species. It's the story of how creatures that could bite through steel, outswim anything in the water, and coordinate complex hunting strategies found themselves helpless against forces beyond their control. But it's also a story of incredible resilience. How? Life not only survived the greatest catastrophe in Earth's history, but used it as an opportunity to evolve even more terrifying predators than before. Before the Great Dying, the Permian oceans were a predator's paradise. The buzzsaw sharks like Helicoprion ruled the open seas with their spiral teeth perfectly designed for shredding cephalopods. Massive predatory fish like Dunkleosteus had given way to increasingly sophisticated marine reptiles and advanced sharks. The mayest diamond sharks. The oceans were warm, oxygen-rich, and teeming with life. Complex food webs supported everything from tiny filter feeders to massive apex predators. Coral reefs covered vast areas, providing nursery grounds for countless species. The marine ecosystem had achieved a level of complexity and stability that had taken hundreds of millions of years to develop. For apex predators like Helicoprion, life was good. They had survived previous extinctions, adapted to changing conditions, and reached what seemed like evolutionary perfection. Their spiral-toothed jaws could process any prey they encountered. Their global distribution meant they had access to resources across entire ocean basins. But evolution's most important lesson is that perfection is always temporary. Scientists generally concede that the Great Dying was triggered after a violent streak of eruptions in the Siberian traps. But calling them eruptions doesn't capture the sheer scale of the catastrophe. These weren't ordinary volcanic events. They were Earth system destroyers. The Siberian traps released more volcanic material than any event in recorded geological history. For over 1 million years, massive floods of lava covered an area larger than Europe. The eruptions released poisonous gases, acid rain, and greenhouse gases on a scale that transformed Earth's entire atmosphere and ocean chemistry. As the volcanoes erupted, they released excessive amounts of carbon dioxide. In turn, ocean oxygen levels dramatically reduced as acidity levels skyrocketed. About 80% of the ocean's oxygen was gone, with some parts of the sea containing zero oxygen, especially the deepest parts of the seafloor. Imagine being a marine predator perfectly adapted to ocean life, and then watching that ocean transform into something alien and hostile. The water itself became poisonous, too acidic for normal biochemistry, too warm for proper oxygen dissolution, and too toxic for the food webs that had supported life for millions of years. For creatures like Helicoprion, which had survived previous extinctions through their adaptability and global distribution, this presented an impossible challenge. They could adapt to changes in prey availability, ocean temperature, or sea level, but they couldn't adapt to an ocean without oxygen. As a TFOVs result, the majority of marine species from this period went extinct due to suffocation, including Helicoprion. Even the buzzsaw sharks, with their perfect predatory adaptations and global success, couldn't survive in an ocean that had turned against life itself. The Great Dying didn't kill randomly, it followed brutal rules that revealed the hidden vulnerabilities of even the most successful predators. Large predators died first. They needed the most energy, consumed the most oxygen, and relied on complex food webs that collapsed early in the crisis. Specialized predators died next. Creatures like Helicoprion that had evolved specific feeding strategies found their prey extinct and their specialized adaptations useless. Generalists survived longer, But even they eventually succumbed as the ocean's chemistry became incompatible with complex life. The only survivors were small, simple organisms with low energy requirements and the ability to tolerate extreme conditions. In terms of marine predators, virtually everything larger than a few feet was wiped out. The ocean was a pretty empty place afterward. This simple statement from paleontologist Nadia Frebisch captures one of the most profound moments in Earth's history. After 500 million years of increasing complexity and predatory sophistication, the oceans were essentially reset to their primordial state. Gone were the armored placoderms, the buzzsaw sharks, the early marine reptiles, and the complex ecosystems they had created. The few survivors found themselves in a simplified world, where the rules of predation had to be rewritten from scratch. But as we've seen with Thalatorchin, this empty ocean also represented unprecedented opportunity. Evolution abhors a vacuum, and the post-extinction seas became laboratories for entirely new types of predatory innovation. The Great Dying revealed that even evolution's most perfect predators had hidden vulnerabilities. Physical perfection meant nothing when the environment itself became hostile. Global distribution couldn't help when the entire planet was affected. Predatory specialization became a liability when ecosystems collapsed. Most importantly, it showed that apex predators are always more vulnerable than they appear. Their position at the top of food webs makes them completely dependent on the stability of everything below them. When that foundation collapses, even the most powerful predators fall. But not for long. The fossil record shows that species returned quickly. The presence of a top predator like Thalatorchin during that time period shows that the system was intact within a relatively short time. Since marine ecosystems build from the bottom of the food chain up, this rapid recovery from near total extinction to apex predators in just 8 million years demonstrates life's incredible resilience. But more than that, it shows that extinction events can actually accelerate evolution by creating opportunities for entirely new types of organisms. The rise of a predator such as Thalatorchin documents the fast recovery and evolution of a modern ecosystem structure after the extinction. The post-extinction oceans didn't just rebuild what they had lost. They created something entirely new. Where previous marine predators relied primarily on armor, brute force, and specialized feeding strategies, the new generation combined intelligence, speed, and behavioral sophistication. The extinction had taught evolution valuable lessons about adaptability and resilience. The Permian-Triassic extinction wasn't the only mass extinction that ocean predators faced. The Endordovian, late Devonian, and Triassic, and end Cretaceous extinctions each presented different challenges and opportunities for marine predator evolution. Each extinction event eliminated certain types of predators while creating opportunities for others. The pattern repeated. Large, specialized predators died first, followed by rapid evolution of new predatory strategies among the survivors. The most famous extinction, the one that killed the dinosaurs 66 million years ago, also devastated marine ecosystems. The massive Mosasaur empire, which had ruled the oceans for 20 million years, was wiped out almost instantly. When the asteroid struck at the end of the Cretaceous, the marine ecosystems that supported the Mosasaur empire collapsed almost instantly. Unlike land animals that could shelter and scavenge, the specialized ocean predators had nowhere to hide. The extinction showed that even the most sophisticated marine predators were vulnerable to sudden, catastrophic changes. The Mosasaur's complete adaptation to marine life, which had been their greatest strength, became their fatal weakness when the ocean itself became hostile. Today's oceans are experiencing what some scientists call the sixth extinction, a mass extinction event caused by human activity. Ocean acidification, warming, plastic pollution, and overfishing are creating conditions that echo past extinction events. Modern marine predators, great whites, orcas, and others are facing challenges similar to those that destroyed their prehistoric counterparts. The difference is that this extinction is happening in decades rather than millennia, giving evolution no time to adapt. The study of prehistoric marine extinctions reveals a fundamental paradox. The very traits that make predators successful also make them vulnerable to extinction. Large size requires abundant prey. Specialization creates dependencies. Position at the top of food webs makes them vulnerable to ecosystem collapse. Every prehistoric marine predator we've examined was perfectly adapted to its environment until that environment changed. Their evolutionary perfection became their evolutionary trap. However, some predatory lineages did survive multiple extinctions. The cartilaginous fish, sharks, and rays have survived every major extinction event for over 400 million years. Their secret: maintaining relatively small sizes, generalist feeding strategies, and flexible physiology. Modern sharks are the descendants of predators that learned the ultimate lesson. In an unpredictable world, adaptability trumps specialization. They gave up being the biggest or most powerful predators in exchange for being the most resilient. Each extinction event the marine predators survived taught evolution new lessons about resilience and adaptation. The predators that emerged from each crisis were more sophisticated, more adaptable, and in many ways more dangerous than their predecessors. The post-extinction innovations, intelligence, social behavior, advanced sensory systems, and behavioral flexibility represent evolution's response to the lesson that physical perfection alone isn't enough for long-term survival. The relationship between ocean predators and mass extinctions reveals evolution's most important truth. Change is the only constant, and the ability to adapt to change is more valuable than any specific adaptation. The greatest marine predators weren't necessarily the biggest or strongest. They were the ones that could survive when the rules of the game changed completely. They represent evolution's ongoing experiment in balancing specialization with adaptability. But the story of oceanic terror doesn't end with past extinctions and ancient predators. As we'll see, the legacy of these prehistoric killers lives on in today's oceans, and their influence extends far beyond what most people realize. The lessons learned from 500 million years of predatory evolution continue to shape marine ecosystems today, and understanding these ancient killers provides crucial insights into the future of our oceans. Chapter 11. The Survivors. You might think that after 500 million years of evolutionary experimentation and multiple mass extinctions, today's oceans would be filled with the most terrifying predators Earth has ever seen. You'd be wrong. The truth is far more sobering. We live in a diminished ocean, populated by the evolutionary remnants of true giants. But don't mistake diminished for harmless. The predators that survived the great extinctions did so for a reason. They represent the ultimate expression of adaptability over specialization, intelligence over brute force, and resilience over perfection. These are evolution's battle-tested survivors, and in many ways, they're more dangerous than their prehistoric ancestors, not because they're bigger or stronger, but because they're smarter. Consider the great white shark, Carcharodon carcharias. At 20 feet and 5,000 pounds, it's a minnow compared to Megalodon's 60-foot, 50-ton frame. But great whites have something Megalodon never developed: perfect adaptability. They can hunt in water barely deep enough to cover their dorsal fins, or dive to depths of 4,000 feet. They can switch between hunting seals, fish, rays, or even other sharks depending on opportunity. Where Megalodon was locked into hunting large whales, great whites are opportunistic generalists. This flexibility allowed their lineage to survive. Every climate change, every extinction event, every ecosystem collapse that wiped out more specialized predators. They're not living fossils. They're evolutionary perfection distilled into its most essential form. The orca, OCEANIC orca, represents perhaps the most sophisticated predator in ocean history. While Leviathan Melville had larger teeth and greater size, modern orcas possess something no prehistoric predator achieved: true cultural evolution. Different orca populations have developed distinct hunting techniques, passed down through generations like human traditions. Some orcas have learned to beach themselves to catch seals, a technique so dangerous that it requires teaching and practice. Others coordinate complex hunting strategies to take down blue whales, creatures 10 times their size. Most remarkably, some populations have developed the ability to hunt great white sharks specifically for their livers, flipping these apex predators upside down to induce tonic immobility before surgically removing the most nutritious organ. This isn't just predation. It's surgical precision guided by cultural knowledge. Orcas represent what happens when intelligence becomes the ultimate predatory weapon. They've achieved something no prehistoric predator managed. They've learned to hunt other apex predators not through size or strength, but through strategy and teamwork. Giant Pacific octopuses and Oroptopus dufflini showcase intelligence in a completely different form. With arms spanning 30 feet and weighing up to 600 pounds, they're the largest invertebrate predators on Earth. But their true terror lies in their problem-solving abilities that rival those of vertebrates. These creatures can open jars, navigate mazes, and use tools with precision that would make early humans jealous. They've been observed using coconut shells as portable shelters, manipulating rocks to create barriers, and even learning to recognize individual humans. Their camouflage abilities are so advanced they can disappear completely in plain sight, changing not just color but texture to match their surroundings. What makes them truly terrifying is their alien intelligence. Where mammals think in ways we can understand, octopuses process information through a distributed nervous system where each arm has its own brain. They represent a completely different approach to intelligence, one that evolution developed independently from vertebrates. Humboldt squid, Doscidicus gigas, known as red devils, demonstrate the terror of coordinated invertebrate predation. Growing up to 6 feet long with tentacles lined with rotating hooks, they hunt in aggressive schools that can number in the hundreds. These aren't the solitary predators of prehistoric seas. These are coordinated pack hunters with communication abilities. They can change color rapidly to communicate with each other during hunts, flashing patterns that coordinate attacks on prey much larger than individual squid. Divers report being surrounded by walls of these creatures, their chromatophores creating light shows as they coordinate their assault. They've been known to attack humans, sperm whales, and even each other with equal enthusiasm. Saltwater crocodiles, Crocodylus porosus, represent the ultimate survivors, living links to the age of marine reptiles. At 23 feet and 2,200 pounds, they're the largest living reptilian predators. But unlike their prehistoric relatives, they've achieved something remarkable. They've learned to exploit both aquatic and terrestrial environments with equal efficiency. These creatures can remain motionless for hours, conserving energy while monitoring vast territories. Their bite force of 3,700 psi approaches that of prehistoric giants, but they combine it with intelligence that allows them to learn individual patterns of prey behavior. They've been observed using tools, demonstrating patience that spans seasons, and showing problem-solving abilities that challenge our understanding of reptilian intelligence. Bull sharks, Tacharhinus lucus, may be the most adaptable predators on Earth. They can transition seamlessly between saltwater and freshwater, hunt in rivers thousands of miles from the ocean, and survive in environments that would kill most marine predators. They represent evolution's answer to the question, what if we created a predator that could hunt anywhere? Their testosterone levels rival those of African elephants in musth, driving aggressive behavior that makes them responsible for more attacks on humans than any other shark species. They don't just hunt, they explore, test, and challenge everything. In their environment, modern sperm whales, Physeter macrocephalus, are the deep-diving champions that put even advanced ichthyosaurs to shame. They routinely dive to depths of 7,000 feet for over an hour, hunting giant squid in complete darkness using echolocation more sophisticated than human sonar. These battles in the abyss sperm whales versus giant squid represent some of the most epic predatory encounters on modern Earth. Sperm whales bear scars from tentacles over 40 feet long, evidence of battles with creatures that remain largely mysterious to science. The most chilling aspect of modern ocean predators isn't their individual capabilities, it's their adaptability. They've survived multiple mass extinctions, adapted to changing climates, and now face the greatest challenge in Earth's history: coexistence with humans. Some, like orcas, are learning to exploit human activities, following fishing boats and learning to steal catch directly from lines. These modern predators represent evolution's ultimate lesson. In an unpredictable world, intelligence and adaptability triumph over size and specialization. They're not the biggest predators in ocean history, but they may be the smartest. And in an ocean increasingly shaped by human activity, intelligence may be the most dangerous predatory weapon of all.